Welcome to the next lecture of the module Data Dimensions, and in this lecture we'll be talking about PCA, that is Principal Component Analysis. PCA is an unsupervised non-parametric statistical technique which is primarily used for data reduction, or I say data dimension reduction. The target is that we need to reduce the dimensions of our data. In case of high dimensionality data, the dataset has a large number of features. So the primary problem associated with high dimensionality is that the model overfits, which reduces the ability to generalize beyond the examples in the training set. So we target to reduce the dimensions of our data. It can also help us to visualize the results or the data itself, right? Because in case of higher dimensional data, the part or the process of training data becomes very expensive, or it's become exponentially hard computationally. So what we try to do is we try to reduce our data to get out the extract of high dimension and to fit it into a lower dimension data. Also, it is used to filter noisy datasets. For example, in case of image compression, so the target is to remove the noisy data, right? So let's see how principal component analysis works. One more thing, that this particular technique, this is an unsupervised model, and there is a lot of math going behind this model. So there are eigenvector, eigenvalues. This kind of mathematics is involved behind this algorithm. So you don't worry about that, you just understand how it works and how it makes our work simpler. Okay, so starting with our lecture, we'll be importing our libraries NumPy, Pandas, Matplotlib, that's the basic one. Remaining one we'll be importing as we need them. So loading the data, libraries, now the data. So I'm again using the dataset that we have used in the previous section, that is the feature selection method. PC also selects the feature efficiently and then performs the work. Okay, so data.head. So as you know, we have to predict the solar radiations. Then the data info, 17,520 entries. Data description, that's. Now we have to clean our data because there is no solar radiation readings before 6 AM and after 6 PM. So we'll be removing this. This is the clean one data before 6 AM. And then I can show you the clean 2 data, that is the data after 6 PM. Okay, so we are dropping both these clean 1 and clean 2 from the original data. So our data is refined now. Let's check the data description. Okay, and now the data head. So now we have total of 9,490 entries with us. Okay, so now what we'll do is we have a clean data. Now we'll prepare a training and testing part for our data set, and then our target is to feed it to a k-mean data. Then I'll be reducing the dimensions so that we can see the plotation of our data. Okay, so for that what we'll do is, now first of all we'll prepare our data, training and testing. So for that I'll say x equals to data dot ilog, and then all the rows. Now columns 4:10. We don't consider this column, we are not considering this column year, month, day, hour, because they are not relevant over here. Okay, and then dot values. Okay, so y equals to data dot ilog, all the rows and only the last column, so that is the 10th column, dot values. Okay, so now we have to reshape our data because it will be in the form of an array. So we want it in the form of a column. So we'll say reshape -1, 1, that is column axis. We want a column axis, so we are reshaping it. Then we will split our data to training and testing part. So from sklearn dot cross validation import, what we have to import is train test split, right? And then xtrain, xtest, y train, y test. Okay, now we'll be using train test split modules. We'll pass our data, input, output, then the ratio, test size equals to, let's say 0.2, and random state, let it be 0. Okay, so here we go. What you can do is you can also use a modern selection module. It will work completely fine. Okay, so our model is, let me show you the X train. So X train, that's like this, because we are taking only these columns 1 2 3 4 5. So 1 2 3 4 5, also the dew point, so 6 columns. Okay, so we are taking 6 columns into consideration. And let me show you the Y train also. Sorry. Okay, so yeah, so that's the final column, that is the global radiation, solar radiation, that is GHI values. Now we'll apply the scale. Now we'll scale our data, because we have different range of values in each column. So as to make it a uniform distribution, we'll apply standard scalar technique over the data. So from sklearn dot pre-processing import standard scalar. Okay, now standard scalar, sorry, wait a second. So standard scalar, let's name it as standard scalar x equals to, copying it, standard scalar, and then we will fit transform our data. So x train equals to scx dot fit transform the data we have, that is x train data. Okay, then the x test value, so x test value equals to scx dot transform, because we have fit our data as per the x train, so we just need to transform that x test data. So x test, okay, so scy equals to standard scalar. Again we have to initialize this because it will perform differently. Okay, so y train equals to similarly scy dot fit transform the data we have, that is y train data. Okay, wait a second, so it's pre-processing. Okay, transform, sorry, yeah. Here we go. So we have scaled our data. Now let's see the data we have now. Now you can see the data is from -1 to 1. Okay, and similarly let me show you the y train we have. So y train is also in the range from -1 to 1. Now we'll apply the clustering technique over our data. Okay, I'll be preparing the clusters from for our data, so as to fixes into a range. What I'm doing is I'll not consider this GHI column. I'm just preparing the clusters which will be suitable for our data. Okay, my basic target is to show you how dimension reduction will work. Okay, so for this, from sklearn dot cluster, we'll import the k-means. Okay, and then k-means equals to k-means. Now the number of clusters we want, initially let's say we want 6 clusters. Okay, don't worry about the technique or how we are using. The target is to show you how PCA will work. Random state, sorry, equals to 6, and then Yep, fine. And then k means equals to k means dot fit. So the training data we have is x train. Here we will not consider y train as we are doing the clustering part. Okay, so here we go, x train. Yep. Now the labels we have, so labels equals to k means dot labels. Okay, and let's print the labels. So these are the labels assigned to our data. So this data instance will be assigned 0 label, and similarly 0 label is 0th cluster. So this is how the stuff works. Also we can check the cluster centers we have. So for that we can say k means equals to cluster centers. Okay, k means dot cluster centers. Okay, print this way. Let me again run it. I have basically changed the terminology. Okay, so it's the cluster centers. Okay, so now I'll be printing the cluster centers. So these are the cluster centers. These are 6 cluster centers on the basis of which other data points are clustered. So these are the centroids of each 6 clusters. Okay, so now you have seen that we have clustered our data. We have used our data and clustered it into 6 clusters. Okay, now the data dimension we have 6 features with us and we are clustering them. So if I need to visualize the result, how can I? It's not possible to plot a 6-dimensional data over here. So what I'll be doing is I'll be converting this data, this 6 featured data, to only 2 dimensions. Okay, so for that what I'll do is I'll use from scikit-learn, yeah, and then using the decomposition module, I'll import the PCA, right? And then PCA will be PCA, and the number of components we want, that is the dimensions we want 2 dimensions, so the number of components equals to 2, right? And then we have to fit transform our data, so we'll say we'll fit our x-train data, and then PCA will transform as per the training data. Okay, so you can if for that it's input. Yeah, so now you can see it's again giving an error, it's x-train. So now using the PCA we have converted our data to 2 components only, right? Let me show you the data we have now. So you can see that we have only 2 dimensions. Initially we were having 6 dimensions, but now we have only 2 dimensions with us. For visualizing, we'll use this PCA converted data since it's a 2-dimensional data only. So now we can plot this data very easily in a 2D graph. So understand this code first. For each data we have, each data instance we have, I am plotting it on the basis of labels we have. So since it's suppose X and Y, so what I am doing is I am plotting each of this data, the 0th column and the 1st column, based on the labels we have. Data will plot according to the cluster it has, right? So what is this PCA is saying? It's saying 0th column and ith row. It's saying 1st column ith row. So I am plotting X and Y, and it will be assigned to cluster 6, C16 if it's a part of 0th cluster, then C26 if it's a part part of first cluster. This label is equal to 0, equal to 1, equal to 2. These are the labels that we have in our data, and we are plotting this x and y values based on the data labels we have. Okay, and then we are setting different colors, different markings, so that it is clearly understandable to you. I'll explain it to you again. What we are doing is we are scattering the data sets. I'm applying a loop for all the data we have. So when the loop will apply, it will give the data. So PC is the data we have, and I is the number of row, and 0 is the 0th column, 1 is the first column. So we are plotting x and y column, and we are saying that if this data belongs to 0th label and this 0, 1, 2 comes from k-means, after applying the clustering, I am saying that if data instance, that is we have reduced using the PCA, if the reduced data instance belong to 0th label, then this data will be classified as C16. If it belongs to second label, it will be C26. So this is how we are plotting x and y, and we are assigning these pairs to the cluster numbers our model has predicted. Pretty easy, right? So now for plotting, let's set the size. So I'll say RC params, then the figure size. So figure dot fig size equals to, let's say 12,10. Okay, and then we have to set the legends as well for the different clusters we have, so that you can clearly know that to which color belongs to which cluster center, right? So for that we'll use legends, right? And then we have to label it. So we have C16, wait, so C16, C26, C36, C46, C56, and C66. Okay, so for each 6 centroids we have 6 different labels. So let's label them. So cluster 0, okay, cluster 1, okay, we don't need so many, it's already done. Yeah, cluster 1, 3, 5, 6, 4, 2. Okay, so we have 6 cluster labels, and now let's set the title of our graph as k-means cluster, right? Now we'll show the data. Just wait for a second, it's loading. Okay, so these are the clusters we have, right? So you can see that we have brought up our 6-dimensional data to just a 2-dimensional space. So these are the clusters. This is how our data is being assigned different clusters. You can see over here. This is not the perfect clusters for our data. You can improvise the k-mean cluster. You can see your code for over 5 or 4 then 3, because you can clearly see that in this case this cluster 5 is just overlapping over the cluster 2, and that cluster 2 is overlapping the cluster 4. So in this case there might be a single cluster which can perfectly fit all the data, right? So you can just check the data by using different hyperparameters in k-mean. So when you're training your k-means over here, you can select different number of clusters and see how the performance of your data is. Okay, and also you can clearly see that initially we were having six dimensional data. After applying PCA, we have a 2D data, and this 2D data is being plotted, or it's being put corresponding to the results of k-mean clusters, and it has been plotted as per the results of k-mean clustering, and then we have a two-dimensional space. So this is how principal component analysis technique works. This is how we can reduce our data dimensions. Okay, before applying k-means also, you can still remove your still reduce your data, and you can use that reduced data corresponding to your labels and can train to your models. This is your choice. I have used PCA here for my visualizing part. You can use your PCA before training to your machine learning model also. Okay, this depends on your choice or the data you are choosing. Which works better, you can choose that technique. Okay, so this was all for this lecture. Thanks for watching this video and keep following.